Suppose I take these two terms, x plus 2 and x plus 3, and multiply them together. How do I do that? Well, there's several possible methods, and one of them is popularly called FOIL. This may be one that you remember. And FOIL stands for first, outside, inside, last. And what that means is that I'm going to distribute my two numbers across the second set of two numbers. So x times x, these are my first terms, gives me x squared. My outside terms give me 3x when I multiply together. My inside terms, 2x. And my last terms, 6. These are like terms. In other words, I can add them together, combine them, and I get my result like this. So just to clean this up, I'll put this back over here, x plus 2, x plus 3. And we see that this and this mean exactly the same thing. They're numerically equal to each other. The point of showing you this is that we're going to work with polynomials that look like this. We're going to work with polynomials that look like this. And each one of these has its advantages in different situations. This is what we call the expanded form, because we take these two factors here and expand them by multiplying them together. This is called the factored form. And it's called the factored form because we take the expanded form and break it up into its factors. Just like if I took the number 30, okay, I could break that into factors of 2 times 3 times 5. Okay, so factored form and expanded form are two sides of the same coin. So the FOIL method is one way to expand a polynomial. There are a couple other methods. I'll show you very quickly the box method. And to do this, what we're going to do is draw a little box, split it into 4. And across the top, I'll put my x plus 2, and down the side, I'll put my x plus 3. Now I could put the x plus 2 on this side and the x plus 3 on the top. It doesn't really matter. The idea is this. At each box, I'm going to look at the row and column heading and multiply those together. So for this first box right here, I have x times x gives me x squared. I have 2 times x for here, gives me 2x. And I'm going to put a plus sign here just to keep track of that. X times plus 3 gives me plus 3x. And plus 3 times 2 in this corner here, plus 6. Okay, so each box just is the intersection of these two things multiplied. So now all I do is take all of those pieces and string them together. I have an x squared, I have a 2x, I have a 3x, and I have a 6, and I get the exact same thing, x squared plus 5x plus 6. So really the process is the same with the box method as the FOIL method. It's just a different way to organize the same process and the same method. So whichever one you like better, you can choose that. There's also a third method that you may consider, and this is called the vertical method. And the reason that this might be useful is just because it looks like multiplication that you've done before. So I'm going to be multiplying these terms together, and so I can take 3 times 2 gives me 6, 2 times x gives me 2x, I have a plus sign in between. Now I go 3 times x, move 1 over like I would with regular multiplication, gives me 3x, and x times x gives me x squared. Add them all up. 2x plus 3x is 5x, x squared. Once again, we get the same result as before. So three possible methods that you can use to expand factored form of a polynomial. Now you may be asking yourself, why would we want to do this? What purpose does this serve? And one answer is that the factored form of a polynomial actually helps us to solve equations. You might remember this guy right here. This was a equation for the volume of a box that we made from a single sheet of material by cutting out corners of size h on a side, square corners, and folding up the box and trying to get a box of maximum volume. So what we did here was took the various values of h and made a graph, and we ended up with something not quite a parabola. It was a polynomial graph, but not a parabola. And these points were 9 at the high end and 0. So this is h. This was our volume. So for that activity, the idea was we wanted to find the maximum point here. But the other thing we had to worry about was what values of h do we really want to consider? And we found that our domain for this was the values of h between 0 and 9. So what's magical about these particular numbers? Well, that's where the graph is crossing the x-axis. And in fact, if we were to graph this polynomial on the calculator, we would see that it actually goes off something like this, and we actually have another 0, another x-intercept over here at h equals 15. But for a variety of reasons, these are the only values that work. These are values that give us a positive volume. These are values that are within the range of numbers that make sense for our problem. But when we're trying to solve polynomial equations, we may want different parts of the polynomial. We may want the whole thing. So we need to find out, how do we get these numbers here? Well, it turns out that the factored form and the zeros are closely related. And so let's see how that works. If you think about trying to solve this for where does it cross the x-axis, what we're doing is trying to say, where is this graph equal to 0? Where is the y value, the function value, equal to 0? So in order to solve this, we want to recognize a pattern here, and the pattern is this. If I have three things multiplied that equals 0, 1, 2, 3 things multiplied that equals 0, one of three things has to be true. This has to equal 0, regardless of what this is. 0 times number gives me 0. This has to be 0, regardless of what these numbers are. Or this has to be 0, regardless of what these numbers are. So if I multiply three numbers together and get 0 for an answer, I know that at least one of them has to be equal to 0. Now, how does this help us to solve this equation? Well, actually it makes it very simple, because now we can look at each piece of this thing by itself. And you notice that even though we have a complex polynomial, we've broken it down into simple parts here. And we know now, for example, that this piece could equal 0. This piece could equal 0. Or this piece could equal 0. Well, this is already solved. H equals 0 actually was one of the points that we had. Okay. Now the other 2 points are represented from solving these. And so how can we solve this? Well, I'm going to go ahead and add 18 to both sides here. That's going to give me negative 2h equals, subtract 18 from both sides, equals negative 18. H equals, divide both sides by negative 2. That's going to give me negative 18 over negative 2, which is h equals 9. Okay, that was our other number that we had found. And the last one is h equals 15, if you remember the graph. And so we'll just solve this one here. Maybe add h to both sides. We get 15 on this side, h on this side, and sure enough, there's our h equals 15. So this method allows us to solve the polynomial. If we put 0 on the right side here and then use the factored form on this side of the equation, we can set each factor equal to 0 and find out what value of h makes this equal to 0. Let's do one more quick example. Here's another polynomial. We've set this equal to 0, so we want to find the zeros of this polynomial right here. And so once again, we will look at three different things. We have x equals 0, so that one's already done. We have x minus 3 equals 0. If I add 3 to both sides, I get x equals 3. And we have 2x plus 5 equals 0. I'll subtract 5 from both sides and then divide by 2. And I get my three zeros at x equals 0, x equals 3, x equals negative 5 halves. Here's another one. Do the same process. X plus 2 equals 0 leads to x equals negative 2. X plus 3 equals 0 leads to x equals negative 3. X minus 8 equals 0 leads to x equals positive 8. And so there's a pattern here also that you might recognize, a little bit of a shortcut. When you have just x by itself without a number in front of it, you can just take the opposite sign of the number here and get your result. So x plus 2 leads to x equals negative 2. This factor x plus 3 leads to x equals negative 3. X minus 8 leads to x equals positive 8. Now again, you have to be careful, because if you get something like this where you have a number in front of x, you really have to go the full distance here. Write it out equal to 0. Do the math. It's only a couple of extra steps, and I recommend, until you get comfortable with recognizing the difference, that you just go ahead and write the equations. These are very, very simple to solve. So it might take you a little bit longer, but you'll be able to get the correct answer every time. Once you recognize when you can and can't, let's say, jump to a conclusion, then you're in a position to be able to take a look at this and come up with the numbers very quickly. Now there's one more thing we can do, and that would be actually to work backward from a list of zeros. If I was told I have zeros at x equals 3, x equals minus 9, and x equals 2/3, how could I put together a possible polynomial that meets this criteria? So these are all zeros. And the answer is really simple again with this. I'm going to just say, well, if x equals 3, then how can I make a factor that equals 0 when x equals 3? Well, very simple. X minus 3 is equal to 0 when x equals 3. X plus 9 is 0 when x equals 9. And x minus 2/3 equals 0 when x equals positive 2/3. So taking a list of zeros and converting it into a possible polynomial does the trick. Now I could put a number like 3 out here and not change the zeros, because I know this could be 0, this could be 0, this could be 0. Well, this is never 0, but as long as one of these is, this is still equal to 0. So it may be that you would see this polynomial with a slight change to it. Okay, so compare these two here. And what do we have? We have x equals 3. We have x equals negative 9. We have 3x minus 2 equals 0. Let's solve that. 3x equals 2, x equals 2/3. It's the exact same list. It's just that my graph is going to look a little bit different, passing through the same points on the x-axis, but having a little bit different look in the vertical direction.